Hi, everyone. As he said, my name is Eric Christopher. I'm currently the debug information maintainer or something like that. Mostly it means that I'm one of the very few people that actually cares about debug information in the compiler right now. And I'm going to tell you kind of where we are, where we've been, what kind of plans we've got for the future. Some bugs need to be fixed, hopefully talk about a few things you care about, and go on from there. So what works today? I'm going to go over, in general, what works as far as debugging. I'm going to use the GDB test suite primarily as my guideline and use a few different other things to illuminate what works and what doesn't. So, as I said, what doesn't work, and then where are we going and why are we in this silly handbasket? So I think this really encapsulates debugging a few years ago. At some point down here on the 7 range, you were just crying trying to use clang and LLVM to debug, or you were over here at too serious for numbers and blood coming from everywhere and you couldn't actually get anything done. You probably debugged something about like this, which you may or may not be able to read. Basically, you debugged using printf or asserts. We've come a little bit of a ways from there. Hopefully sometime we're, hi, we can debug. Or maybe we're like, this isn't quite working, and hopefully that's the optimized side of things, and this is the unoptimized side of things, and we're trying to get everything moving towards the left. So what really works? Debugging actually does work. It works for C, it works for C++, it works for Objective-C++, it works for Objective-C. It works for 97% of the GDB test suite. We pass the vast majority of GDB tests. It passes 100% of the LLDB test suite. Depending on what day of the week it is, we may be failing one. And they usually fix their bug. So speaking of things that are done, how about C++11? Because we haven't had too much in the way of front-endy talks here other than Daniel and Manuel coming up. So these things are done, all of these. R-value references, enum classes, enums, some more enums. A lot of enum changes in C++11. Unions with special member functions, inline namespaces, null pointer, all these lambdas, mostly. We'll talk about that here in a second. So all of the basic things that you need to debug LLVM, clang, LLD, which uses C++11 pretty heavily, all of these things, it mostly works. And Michael will correct me if you can't actually debug LLD. So what doesn't work? Well, stabs. All right, that's in the GDB test suite. I don't care. Unused types. If you, as Sylvester was talking about in his talk earlier, if you ask for don't eliminate unused types, well, we don't support not eliminating unused types due to the way we generate debug information. We basically walk the things that are used as we co-generate them and emit debug information. So if we're not code-genning it, then we're not going to have a type to emit. Patches are welcome. I'd love to see it. It'll happen eventually, but it's not that important except for a couple of cases. C++ template edge cases. Templates work. You can debug templates. There are some edge cases. There are some bugs. We'll talk about those. Labels. All right, there's no debug information for labels. Turns out you can actually use labels in there. Line info for constants. All right, not too bad. Unused struct parameters. Okay, that's getting a little more serious. I really will talk about that here in a second. That's an actual bug that needs to be fixed. TLS variables. Another bug that needs to be fixed. We don't actually support emitting proper locations for thread local storage yet. Very much needs to be fixed. And then there's what I like to call line break interpretations. So the GDB test suite often tests things by basically putting a breakpoint at a line number in a file. Usually works, except if there's nothing on that line. Sometimes we're not emitting line information for it, and GCC is. It's a comparison. How do you feel about where your cleanups end up being broken, that kind of stuff? It's all a matter of interpretation. So ultimately, we've got some problems, and this is one of the bigger ones. So let's say you've got some code like this. You've got a function. You'd like to know the type of your function. Well, what you should get is something that looks like this, right? It's a foo and an int. You said it was a foo and an int. No, we're not going to do that right now. It's a bug. It'll be fixed. Referenced constants, you didn't want that. All right, so it doesn't work. C++ 11 debugging support isn't quite complete yet. We're missing some dwarf 4 features. I'll talk about those in a little bit more detail. And optimized and LTO debugging is interesting. So, where are we going? Well, we're going to continue working on C++ 11 debugging in the immediate future. Atomic types, template aliases, user-defined literals, and the note from earlier. We don't have a current way of emitting a captured this. So if you print this inside your Lambda and you get a value and you wonder why doesn't that match anything, that's because it's the this of the anonymous function for your Lambda. Yeah, it's not very useful, but it is technically this. In the immediate term, though, we're going to finish off dwarf 4 full feature support. Basically, everything in the dwarf standard, going to finish it. There's going to be dwarf 5 fission, which is something Michael alluded to a couple minutes ago. It involves reorganizing how we emit things in debug information. It helps linking immensely. Talk about it shortly. And then we've got a proposal coming up for dwarf 5 as well for accelerated access. And we'll talk about that here in a second too. So dwarf 4. Dwarf 4 was, in addition to adding C++ 11 support, it really was about shrinking everything. How can we make debug info smaller via the encodings or just getting rid of more debug information? So one of the ways they did this was type units, which is basically encapsulating all of the information for a particular type, putting in its own special unit in another section, not quite the section comdat stuff that you'll get under ELF, but it's actually a separate debug information entity. Getting a hash of it, and then allowing the linker or some other tool to unique based on that hash. Pretty useful. We don't support it yet. We probably should, because you can actually start getting rid of a bunch of debug information as you're linking it when you do that. Encoding changes. There were tons of encoding changes or encoding suggestions about how you can shrink the size of your debug information. Also, there are compression techniques. We'll be implementing all of these. We would love some help. And by we, it's me and a couple of other guys now. So fission. Michael talked about this a little bit. It's all about splitting debug information into multiple files. This has happened a little bit before. HP had a method similar to this. Apple has a similar method. A couple of other companies, I think Sun had one. I have no idea how any of the other companies do it, but it's all about splitting debug information. We have a complete implementation of this, and it's submitted to committee for standardization. So what we really mean is that, so when I say we're splitting things, I mean it's actually writing out 2 different object files at the same time. Caveat, we don't actually write out 2 object files at the same time. We use obfcopy to split it out. But you can have it out. And what this means is that the linker itself doesn't have to link debug information. So if all you want to do is compile and run your quick binary as fast as possible, this speeds that up immensely, especially on systems that actually do link all of your debug information. Mac users, you don't have to worry about that. And then later, if you really want to debug, it's still there sitting in these what we call dsym files off to the side, and you don't have to worry about linking everything together if you want it. If you'd like to save it for archival purposes, of course, you can do all the final link and get all of your debug information linked together, store it off to the side, and you can actually even do that in a parallel manner. So the accelerated access that I mentioned is all about speeding up debugger access to named entities and debug information. Basically, it replaces pub names and pub types that were linked together using a couple of other interesting things. There's the GDB index that the GDB guy in the room is looking at me about. So this replaces GDB index in something that's a little more dwarf. We'll call it more dwarf. It basically uses dwarf forms, dwarf encoding, bytes, and that's about it. And it's actually a very portable implementation of a hash table that happens to be optimized for debuggers as opposed to just a normal hash table, right? So we also have a complete implementation of this in Clang. I did that probably about a year ago before we were bringing it up for standardization. And it sped up and reduced memory usage of LLDB, Apple's debugger, by huge amounts. Especially when you're doing things like debugging on an embedded target, where you're actually running your debugger on your embedded target, like, you know, your embedded target. You're not using up all the memory on the device just to run the debugger. So you don't have to, you know, as you're loading and looking for symbols, you don't have to sit there and page through a bunch of different debug information. You can go right to what you need. It's also been submitted to committee. We'll be discussing it next month. There is some documentation that's mostly correct up on the LLVM website. It's under the debugger, source level debugging set, and be happy to talk to anyone about it if they've got any issues. As I said, it's accelerated access. It's made for memory usage. So it's very compact tables. It's made to basically take it from looking for one thing and in fact optimizing for the fact that you're assuming that the item that you're looking for is in fact not there. You're assuming that the user isn't sure which object file the symbol that they're looking for is in, and it optimizes for that. It's extensible, yet it has strictly specified contents. So these things go into this table, these things go into this table, except the data that the payload data that you have in your hash table is very extensible, and you can have as much information as you'd like up to the entire die. Right now, we just do a pointer to the die and enables you to read a specific die very quickly. So that was all of the stuff that we're planning on doing or have done recently. Now there's this big elephant of LTO in particular and optimized code in general. Well, we'd like to shrink that a little bit. So the two biggest things right now that we have for LTO and optimized code are variable tracking, figuring out what's where when we're optimizing, and type merging. Now, I don't remember who it was the other day that mentioned about the obscene memory usage when trying to use LTO with LLVM, but that's probably what it was. So let's have a segue here real fast, because I'm sure you're all interested in how LLVMIR represents debug information. So we've got a variable. It's a class with an int. It looks like that.
Wait, what?
Yes. That's what just the debug information for that looks like. Yeah. It's actually pretty, you wonder why debug information is so big. This pretty much directly maps down to dwarf debug information. So that's how big dwarf is, except with a byte instead of, you know, text. So let's talk about where type merging is. So I'm going to bring out a couple of particular things. This line and this line. The top line defines the variable, defines A. It says basically you've got some gobbledygook, some line numbers, a name, don't ask, a reference to some other piece of metadata, a number and reference to, well, okay, this next piece of metadata, and then the type. All right, so this next piece of metadata has some more references all around, a name, some more references, and some sizes. Okay, you know, references are good. We're pointing, we're not duplicating information, right? All right, so let's talk about this again. So you've got two of these files. Remember that these things were numbered? So, right. 6 isn't necessarily going to be 6 when you link both of these together. And in fact, 4 is probably not going to be 4 either when you link them together. And so what's happening is that as the linking machinery tries with its little heart to link all of this information you've just asked for it, you get ridiculous amounts of duplicates, you get your memory blowing up, and that's what's going on. So I actually have a plan on how to fix this. It involves removing a bunch of references. I have a prototype patch for it. I need some time to work on it, and that'll happen after all these other things. In the meantime, I would like to ask all of you, or at least suggest that you use line tables only. Yes, it's a silly workaround, but for those of you who really just want a backtrace when your program crashes, line tables only is pretty good. It's line tables and some minimal dies. Basically, it's enough dies to get you inlining information when your program crashes and you've inlined all over the place. It's enough for everything, a debugger or everything else, to walk back up and give you your full backtrace. So it's pretty handy. The LLVM symbolizer that ASAN uses is checked in and uses all of this. So that's how you turn it on. It's pretty easy. Makes your LTO links go much faster and more plausibly. So back to modules. Rough segue. So we've got plenty of ideas on how we're going to deal with modules, but we don't have anything concrete on how we're going to debug modules. There's a lot of ideas. I don't know if any of you were at the last LLVM conference, but Doug Greger got up, talked a lot about modules, talked about a bunch of ideas, one of which was storing Clang's ASTs off to the side. At least for the types. You've got all these ASTs, you're storing them off to the side. You can have the debugger understand and parse these ASTs to have ridiculously full type information of the type that only the front end can provide. There's some problems with that. It's a great idea for quick turnaround debugging, but well, you need something for your line table, so we'll probably use dwarf for that. So while we're emitting dwarf, we're probably going to want more dwarf for archival purposes. I don't know about you, but sometimes I want type information for a binary 6 months down the road and not 6 seconds down the road. And so we're probably going to need to figure out a way to actually do debugging for C++ modules as well. I assume anyone knows what modules are. If not, Doug Greger did a brilliant talk. It's published on the website, talk and everything. So I'm sure all of you are breathlessly waiting, and I believe it's probably breathlessly waiting, on how you can help. Well, you can implement those last few C++ 11 features. I would love for a solution to capture this. PR 14330, it's the magic number that contains everything that's currently failing in the GDB test suite. It's actually a master bug that contains everything that's currently failing in the GDB test suite.
You're playing with the sound.
I'm playing with the sound. Someone's playing with the sound. You can identify and report bugs. I honestly can't fix them if I don't know about them. And that's been the biggest problem. I hear lots of complaints. Oh, debugging is awful. Debugging is terrible. Is it? I don't know. Let me know. Discover size optimizations. I really don't know if where our debug information is huge. I hear and know that it's huge in comparison to GCCs. I don't know exactly where. I can start implementing all the dwarf 4 size compression stuff, but what's the particular low-hanging fruit or what's the particular one? I'm not sure. I'll know if you tell me. You can provide donuts. I'm an engineer. I'm based on sugar. I will happily eat donuts for fixing your debug information problems. And with that, questions? Oh man, Diego.
You said you were going to talk about variable tracking and you didn't.
No, I didn't say I was going to talk about variable tracking. I cleverly avoided saying that I was going to talk about variable tracking. So what needs to happen with variable tracking is we're going to need to add in support in every single optimization pass to keep the variables around and not remove them.
You're going to implement the Brazilian technique?
Probably, yeah.
Oh, sorry, no.
It's the one that Alexander Oliva did a few years back. It's probably what we're going to need to do, yes.
It's a very invasive to the optimizers, but it actually is very good. Everything the optimizer does needs to be annotated in the IL. And so when something disappears, the debugger knows. And that's O2 debugging in GCC has gotten better because of this, but everybody hates it because it's invasive in the optimizers.
Right. So I'm sure there will be a nice rumble on the list at some point. And that's why I didn't talk about VAR tracking, is because there are a couple of different ways we could do it, and that's probably the easiest and best. And what's going to end up is hopefully someone will come up with another brilliant idea, or we're going to have to argue a lot. And it's going to come down to how much people care about optimized debugging. You care, you don't care, O0 is good enough. All of you care way too much about this. Okay, that's not good. Next.
Debug Info captures some information on source language program that LLVMIR actually does not have. An example, type-based alias analysis. Of course, it emits its own metadata information.
Right.
But the same information can be captured, can be got from Debug Info, right? And much more. So the question is, have you explored usage of Debug Info for other purposes that requires knowledge on source, on source program, like language-dependent optimizations?
Historically, we've tried to avoid language-dependent optimizations in the back end, outside of named functions and named entities and things like that. We could check the particular thing, but I think Chandler and Jacob have proved that we have enough to do as far as optimizations in the back end right now, and we can handle most of the ways that we translate from language semantics to a better canonicalized IR without needing to bring language-specific transforms into it. Those transforms might be better off in the front end. I know that's heresy to all the front end guys, but if you really want to transform it, maybe hack the trees a little bit before they come out. I don't know. Personal opinion, you can hand it to Chandler. Yeah, exactly.
I'm not going to express any opinion about that right now. So back to Debug Info.
Damn it.
So Eric, how would a naive, an unenlightened developer who likes to play with LLVM and Clang actually go about filing a useful bug report about bad debug information?
Right. Okay. So there are a few different ways. One, we honestly could use your entire program. That sucks, but we need some sort of reduced test case, ideally. If not, a snippet of the source code that hopefully compiles, and you can show where the debug information is going wrong. Now, we provide tools associated with LLVM to actually dump all of the dwarf debug information. You can take a look through that. But if you don't know how any of that works, that's going to be a huge undertaking just to understand it. So the best way is to provide like a GDB, LLDB, some debugger session, something that compiles, or the actual binary itself, and we can take a look at it.
So I just want to make sure I understand correctly what I would need to provide.
Yes.
I run GDB, bad things happen.
Yep.
Right? You need the binary that I was running GDB over.
Yep.
All of the source code, or at least the source code to the relevant functions where bad things happened.
Yep.
And how that source code was compiled into an object file that was part of this final binary.
Yep.
Would you be okay with just the object file, or do you really need the entire binary?
I don't necessarily need the entire binary, but it's hard to verify I've fixed something without it.
Cool. Thank you.
Fuck. I think I have a bug report.
So we've seen over the last couple of years the DI builder gradually grow into an API that's actually quite nice for front ends to generate the debug info. Do we have anything analogous for optimizers to use to preserve debug info without having every optimization be written by someone who is able to read the whole dwarf spec?
Nope.
Okay.
Remember the variable tracking we were just talking about? Yeah, we're going to need to do something like that in order. It'll probably, I don't know, quick off the cuff guess is that we're probably going to need to change IR builder, which people are mostly using in their passes to handle, like I would like to build some IR that would replace this IR and change the debug information accordingly, and we'll want to do that underneath the covers somehow, is probably how I imagine that going. At least the most useful abstraction I can come up with. But there's nothing right now to handle how debug information changes in the back end. Usually replace all uses will replace most of the uses, but it starts to go a little wonky sometimes.
So why would you want to read the dwarf spec?
Hey, it's way more readable than the C++ spec. All the way back there.
Yes. What do you consider a bug in debug info? I mean, for instance, if I have a variable I cannot track after optimization, and another good compiler can give me the right information for tracking that variable even after optimization, is it a bug?
It's probably a bug. Honestly, right now it's probably a low priority bug with if it's with optimization. As you noticed, I have enough O0 problems to deal with first. But probably in order or getting as far as severity in my mind are okay, severity, okay, the debug emitter crashes. Yeah, that's the worst probably. Or you crash GDB with it. Either I care or GDB or both of us care. So if you're getting the wrong information out of the debugger, that's when I really care the most. Like if instead of it saying optimized out for your variable location, it actually gave you 4 and the answer was a pointer off into space, I care a lot about that. It shouldn't actually be wrong if it's there. If the variable's been actually optimized out, I mean, you're going to have to check the emitted assembly code and find out, well, is it actually there? Did we remove that variable completely? And there's just no hope of reconstructing the debug information. Honestly, depending on whatever that other compiler is, then they have ways of variable tracking that I don't yet. So yes, please file it. I don't promise it will get fixed anytime soon, but it's nice to know what's there and what problems exist.
Yeah, hopefully it's already fixed. It's something I submitted a while ago, and I got the answer that what would you expect at O2, where 2 other compiler can track that variable and LLVM don't. Thank you.
I feel like I'm getting trolled by my coworkers here a lot.
I'm just curious, have you looked at the debug info generated by Chrome? Oh, I mean for Chrome?
Yes, it's enormous.
Yeah.
It's ridiculously huge,
Yeah.
and I have no idea why.
Okay, that was my question.
Yeah, I don't know why. I've poked Jeffrey into trying to give me a little bit more information. But that's one of those times when I would like to know what's bigger. I know our line tables are a little larger, but that doesn't explain that kind of size increase. And some of our debug information's larger, and we don't have all of the debug information for some types. So that really concerns me that we're already bigger in cases like that. So knowing about those bugs or knowing about where we're larger and why would enable us to start handling these a little faster. So if you can point to just an object file of this is huge, and this is not with some other compiler, that's actually a good point to Chandler's question of what can you file. If you have debug information produced, produced by GCC and debug information produced by Clang, and Clang's is 4 times as large, and you didn't compress the debug information sections with zlib, I really want to know. So all you have to do is, if you just provide both object files, I can take a look and figure out what's wrong from there.
Okay, thanks.
And no one else has any problems debugging, so it's great. Anyone else? Oh, 2 more.
Any plans to support Microsoft-style PDB files?
I don't have any plans to support Microsoft's PDB file. I got nothing.
Yeah, I noticed that GCC recently added OG,
Yes.
which my understanding is disables optimizations that hurt the debugging experience. Do you have any opinions on that, and whether it would be good for LLVM to do something similar?
I think ideally I'd like 01 to do that, but calling it OG is also fine. Ideally, I'd like to see 01 contain optimizations that both speed up how fast we can get code out there, speed up the runtime of your quickly generated binary, and make sure not to degrade the debug experience as much as possible. So yes, I think it's actually a pretty good idea. I'd love to see it. I will happily review such a patch. Going once, going twice.
Don't have debug support for macros.
We already have debug support for macOS.
You do?
Yeah.
Macros.
Oh, macros.
Yes.
Oh, God. Yeah. Oh, God. You're right. I didn't mention that, did I? Yeah. No. Oh, okay. He can answer this. Sweet. I can't answer this. I'm not planning on doing it.
Don't use macros.
Yeah, I have no plans to implement macro support. If you really want to, I will happily review such a patch, but don't use macros. Yeah. Don't use macros that are that deeply nested. So, anything else? Well, thank you very much, everyone.